Hi guys, we're doing 7.172 notes. So for each of the following, we need to be able to make a table and a graph and list the domain and range. So we're gearing up to talk about the parent function for exponential functions. And actually this one right here, y equals 2 to the x, is going to be our parent function. So there's some things about exponentials. A's can't be 0. If A is 0, then that zeroes out everything, right? B has to be greater than 0, and B can't be 1, because if it was, then we'd have something very linear, right? All right, so we've got, this is going to be our parent function, just future reference. We're going to be using this later to transform some things. So y equals 2 to the x is going to be the parent function. When you make your table, it's just like as always, right? We got x's and y's. Let's start with -2. So remember, if I raise 2 to the -2 power, the negative is going to be flipping, so it's really 1 over 2 squared, which gives back 1/4, right? If I put in -1, 2 to the -1 power gives back 1/2. Anything to the 0 power is 1, right? If I throw 1 in where x is, now I have 2 to the first, which is just 2. And if I put in 2, I get back 4. And if I put in 3, 3 is 2 to the third power, which is 2 times 2 times 2, so I get back 8. And actually, these are the set of points that we're going to have to memorize for our critical points for when we start transforming. All right, so the domain and range on this function is, as you notice, even when I talk about negative x values, I get back fractions, right? They're getting smaller and smaller the more negative I get. So I never touch 0, but I can put in any number I want in for x. So that means the domain is all real numbers. And then for the range, we're going to have 0 to infinity. So if we graph that, actually, I'm going to graph all of them at the end so you can kind of compare all of them. All right, so y equals 3x, we make a similar table, right? So practicing our exponent rules, right? If we put in -2, right, that means it is 1 over 3 squared, which gives back 1/9. If I put in -1, I get back 1/3. If I put in 0, I get back 1. If I put in 1, I get back 3. And if I put in 2, I get back 9. So we have this again, where even if I put in negative values for x, my y values are not going to be negative. They're going to be smaller and smaller to 0. So you can plug in whatever you want for x's, and my domain is not going to be 0 or smaller. Okay, this one I want you to think of as a fraction, so that we can complete our table, because we're not good at doing decimals. So if we do that, right, when I do -2 for my power here, 1/2 raised to the -2 power, right? I'm going to kind of write this out because this can get kind of confusing, right? Negative power means we're going to take this and we're going to actually flip it to the top. So really this is like saying 2 squared, which gives back 4. So if I put in a -1, right, we're going to flip it to the top. It's really like saying 2 to the first, right? Anything to the 0 power is 1. If I put in 1, I get back half. If I put in 2, I get back 1/4, and so on. All right, so again, we have this. This is kind of like the opposite direction from our other examples, but the domain still can be anything we want, and range is still not touching 0, and we're approaching infinity. Okay, so the graphs of these looks like this, right? So this is your parent function here in green. So this is my parent function, right? And if I change what is being raised to powers, you can see that it makes the slope or the curve here, how it changes the curve, right? So it makes it steeper. If it's smaller, it makes it less steep for the curve here. All right, so the general form of an exponential function takes on this. And remember, these values mean something when we start transforming it, right? So for application-wise, though, this A represents initial amount. is talking about kind of growth or decay. So think back to your buzz bug activity. The initial amount was how many bugs you started with in the box. And so when you wrote out your equation, it was really close to 2 or 5 because that's what it was for us in our lab. Then for the growth decay, the number that was being raised to a power in your lab for buzz bugs was close to 1.5 because we remember we talked about how it was the probability of being heads or tails, right? And we were growing, so it was 1.5. And then X is going to be over time. So for applications, that's what those positions mean. Now for growth and decay, we need to talk about it a little bit more. How do I know if something is growing or how do I know if it's decreasing is the amount there. So if it is growing, if it is how do you know if this function is growing or decreasing? It's a growth function if b is greater than 1. That makes things grow, right? Kind of like similar to scale factors in geometry, right? It's decreasing if b is somewhere between 0 and 1. So I don't want you to just jump to the conclusion it's a fraction, right? Because 5/4 is a fraction, but 5/4 is greater than 1, right? But so if we have a value for b that's somewhere between 0 and 1, this could be half, this could be 3/4, this could be 0.2, right? That would be decreasing function. Okay, so let's apply this into a word problem. All right, so we're identifying each function as first as either a growth or a decay. So remember that comes back to my b value. So I need to be looking at my b value for that. Then I'm supposed to answer what is the function's percent increase or decrease. Okay, so looking at my first example, right? First I have to answer growth or decay. So I'm looking at my b value. My b value is greater than 1, which means it is growth. When it asks for the percent increase or decrease, I have to think about it in terms of how far away this number is from 1, because remember 100% as a number is 1. This is 1.73. So that means we're growing by a factor of 1.73 minus 1, which is 0.73. Change that to a percent, right, is equal to 73%. This one is 1.5, which is greater than 1. So that falls under the growth category. How much is it growing by? 1.5 minus 1 is 0.5. We move it over 2 places to get the percentage, right? So that equals 50%. This one has a b that is in between 0 and 1. So this is an example of decay. Again, we have to do the 1 minus. So 1 minus 0.65 gives back 0.35. So that's by 35%. Okay, the next one, 3/4, is another decay because that value of b is between 0 and 1. 1 minus 3/4. 3/4 is really 0.75, right? So that is 0.25. Change it to a percent, makes 25%. This number is in between 0 and 1, so again, it's a decay. 1 minus 0.5 is 0.5. Change it to a percentage, equals 50%. This one, let's slow down a little bit, right? Because it feels like we're missing something. Okay, so remember we have, it's supposed to be a b to the x power. A b to the x power. So 6 is really a b value. A value is that invisible 1. So my b value is 6, which is definitely in the growth category because it's bigger than 1. So this is growth, right? We're going to do the same thing. We're going to do 6 minus 1 because it's greater than my 100%, right? Just like we've done over here, right? And then we get back 5. I still have to change it to a percentage though, so that makes 500%. Okay, so now applying it to some word problems. We've got student enrollment of Reagan is 2,100, aka this is my initial amount. Initial amount is the letter A, right? In the year 2000 and has increased by 6.5% per year. So this is my sort of my B value, right? We're gonna have to analyze that a little bit more. If this growth continued and we didn't open Johnson High School, what would Reagan enrollment be in 2015? So I've got a time frame between 2000 and 2015. So we're talking about time over 15 years. All right, so we identified A, the initial amount was 2,100. My B as a percentage is 6.5%, and we're talking about growth. So remember on our growth ones, we did 1 plus 6.5%, right? And so if I change that into a number, 6.5% into a number, I move it this way for the decimal, so we get 1.065 as a number. So my B value is actually 1.065 because we have to convert percent to a number. All right, X is talking about time frame. My time frame is over 15 years. Okay, so what does Y equal, right? As a function, right? My function is supposed to be a b to the x power. We're going to substitute 2,100 for a. My b value is 1.065. My x value is 15. So we're going to use that function and input that into the calculator, right? Should look like that, right? And then I get this back. And remember, our final answer is talking about number of students. What would the enrollment be like? So remember, we're not going to have 0.86 people, so we're going to round that to 5,401 students. Like that. All right, so next example is about a car, right? The car was bought for this. This is your initial amount, or A, right? It begins to depreciate after you drive it off the lot and continues to depreciate at 20%. So for my B value, instead of doing plus, we're going to minus because we're talking about decreasing. We're doing decrease of 20%. This as a number, remember we're going to have to move over the decimal place. So we got 1 minus 0.2, which is 0.8. So my B value is actually 0.8. What will Miss Eddie's car be worth in 6 years? So there's my time, 6. So when I substitute into the equation, right, I have 32,000. That's my A, right? Next comes B. B is 0.8, and I'm raising it to the x power. So that's what it looks like substituting into the function. Okay, that's what it looks like when you substitute into the calculator. And remember, our answer is talking about dollars, so we're going to round appropriately for dollars. So $8,388.61.